Hello again, and welcome to Advanced Physics for High School students. This is Lesson 80, and it is entitled Bernoulli's Equation. We now arrive at one of the last new topics in this course of Advanced Physics for High School students. The last topic we'll study in fluid mechanics, the topic of Bernoulli's principle, or Bernoulli's equation. The famous Bernoulli family, originally of Antwerp in Belgium, the paterfamilia, fled to Basel, Switzerland, escaping the Protestant persecutions of the Counter-Reformation, and following him, several generations of offspring who distinguished themselves mathematically and scientifically. The most famous three include two brothers, Jakob and Johann, and a son, Daniel, to whom Bernoulli's equation belongs. Daniel spent time teaching mathematics in St. Petersburg in Russia before returning to his home in Basel, where he, at the local university, held professorships in botany, anatomy, philosophy, and physics, some calling him the founder of mathematical physics. Newton might quibble about that designation. Nonetheless, it was Daniel Bernoulli who in 1738 published Hydrodynamics, a work on pure and applied fluid motion, in which appears, among other things, a proposal for the propulsion of ships by the forcible ejection of water from the stern, the forerunner of a modern fixture in today's watercraft. The theorem in fluid mechanics known as Bernoulli's equation also appears in this work, and it's this topic of Bernoulli's equation that occupies us today. Bernoulli's equation relates quantities about moving ideal fluids in containers. The containers might be pipes carrying heated or chilled water to ventilation systems around buildings at our schools. They might be elevated tanks that supply pipelines, such as water towers or oil refineries. They might be hoses supplying firefighters with water to put out a blaze. The equation emerges from the work-energy principle and the conservation of energy. Here is the equation in the form that's likely to be most useful to you, where P is the absolute fluid pressure, the force per area that is exerted on the fluid. Rho is the density of the fluid. G is the acceleration due to gravity. Y is the elevation of the center line of the container of the fluid. In this case, in this diagram, you see the center line is elevated above some y equals 0 level down kind of at the bottom of the page. V is the fluid's speed at the point in question. The work in Bernoulli's equation appears in the pressure term. The gravitational potential energy appears in the term that contains the elevation, and the kinetic energy appears in the term that contains the fluid speed. If you combine this, Bernoulli's equation, with the equation of continuity back in Lesson 76, where A stands for the cross-sectional area of the container and V is the speed of the fluid in the container, these two equations will be ones that you solve for most of the hydrodynamic problems that you're going to encounter on the AP Physics exam. You're not going to be asked to derive these equations, but you will be asked perhaps to identify the work and the potential and kinetic energy terms in Bernoulli's equation. Let's apply Bernoulli's equation to some numerical problems. Here's the first one that's in your textbook. Example 80.1. Water, whose density is 1,000 kilograms per cubic meter, flows through a pipe with a flow rate of 0.8 cubic meters per second. The cross-sectional area of the pipe at point 1 is 1/4 of the square meter, and the pressure is 5.2 Pascal. The cross-sectional area of the pipe at point 2 is 4/10 of a square meter. What is the pressure at point 2? Let me remark here that the pressure at point 1, 5.2 pascals, is ridiculously small, but this is the number that your authors give us. This is the number we're going to use to solve this problem. We're given the volume flow rate, 0.8 cubic meters per second. That's what the R is in Lesson 76. Since we know what the cross-sectional area is at each section of the pipe, then we could actually figure out what the speed of the fluid is in each section of the pipe. I find that the fluid moves at a speed of 3.2 meters per second in section 1 of the pipe, and at only 2.0 meters per second in the second section of the pipe. And this makes sense. If the amount of fluid I have coming in and the amount of fluid going out are the same, then the fluid's going to move faster in the section of the pipe where it is small in diameter, because the same amount of fluid has to pass through each second. Now, let's also notice that the center lines of these two pipes are equal to each other. They correspond to each other. What that means is that there's no elevation change in this pipe, and so there's not going to be any change in the gravitational potential energy that the fluid has when it moves from one section to another. We'll see that that's going to be important when we write down Bernoulli's principle. Let's go ahead and write that down. Since y1 and y2 are the same number, that means I'm going to have a constant term on the left side of the equation that's equal to the same constant term on the right side. So these two terms are going to cancel each other out. Now I'm looking for pressure P2, and I know all the other variables. Let me solve that equation for P2. And let's put in the numbers. I find that the pressure in the second section of the pipe is just over 3,100 Pascal. This problem is a practical problem, say in the case of fire water coming out of a fire hose. So here's another numerical example that is not in your textbook. Water travels through a 9.6 centimeter diameter fire hose with a speed of 1.5 meters per second. The pressure inside the fire hose is about 150 psig, which stands for pounds per square inch gauge pressure. That's about 10 atmospheres gauge pressure, or 11 atmospheres absolute pressure. At the end of the hose, the water flows through a nozzle whose diameter is 2.5 centimeters. What's the speed of the water coming out of the nozzle? Now, here's a problem that has a whole bunch of numbers in it, and let me give you a caution. In this problem, you may not need all these numbers. And likewise, on the AP exam, you may not need numbers as well. So watch and see what it is that you're given and whether it is that you need all the information that's given to you. In this case, what we're trying to find is what is the speed in the smaller section of the nozzle, in this section that's right here. They tell us a whole bunch about this particular situation. For instance, when the water comes out, it's spraying out at atmospheric pressure. You're also told what the pressure is inside the water hose. You're told the diameter of the pipe. In the first section, 9.6 centimeters, and how fast the fluid's moving in that section. You're told what the diameter is of the section of the pipe, and you're trying to figure out how fast is the water coming out. I would suggest that you don't need all the information about the pressures to solve this. You only need the equation of continuity. Let's write that down. Since we know information about all of this, we can solve that equation for V2. Remember, if we model this as a cylinder, then the area is going to be pi r squared. Solve that equation for V2. And now write the area in terms of the radii and put in the numbers. I find that the fluid flows out of the pipe at a speed of 22.1 meters per second. An important note, make sure that if you're given diameters, that you change them into radii. Since the area goes as the square of the radius, if you accidentally put the diameter in, then your ratio is going to be a bit large. So make sure you convert things to radii. Here's another example from your textbook. Example 80.2. Ethyl alcohol with a density of 810 kilograms per cubic meter has a flow rate of 0.24 cubic meters per second through a pipe whose cross-sectional area is 0.060 square meters and in which the pressure is 9.5 times 10 to the 4 Pascal. The center line of the pipe rises 4.0 meters and the area is reduced to 0.02 square meters. What is the fluid pressure in the elevated pipe? Now, why your authors chose ethyl alcohol as the fluid of interest is not clear to me. Maybe this is in some distillery somewhere where they're pumping around various distilled liquors that need to be bottled, but that's beside the point. We can still solve this equation using Bernoulli's principle. Now, they're telling us that in this pipe, we know what the fluid pressure is. So there's some number that's on section 1 of the pipe that has a pressure of 9.5 times 10 to the 4 Pascal. And they're saying, now let's go over to another section of the pipe and let's figure out what the pressure is going to be in that new section of pipe. That's what we're trying to find. Now, we're going to have different speeds of the fluid in section 1 and section 2 because the pipes have different diameter. And I'm going to have the same flow rate going into the pipe as I have coming out of the pipe. So let's use the equation of continuity to figure out what the fluid speed in section 2 of the pipe is going to be. Let's remind ourselves that we're given what the flow rate is through the pipe. It is 0.24 cubic meters per second. And that flow rate is going to be the area of the pipe times the fluid speed in that section of the pipe. They tell us what the cross-sectional areas are, so we can figure out what the speeds are going to be in each of the sections of the pipe. I find that the fluid is moving at a speed of 4 meters per second in section 1 and 12 meters per second in section 2. Let's also notice that the elevation of the first section of the pipe, if we wanted to call y1 equal to 0, then y2 is going to be 4 meters. Now we're trying to figure out what pressure 2 is. I know everything in that equation except P2. Solve Bernoulli's equation for P2. And now substitute in the numbers. And now put the numbers into your calculator. I find that the pressure in the second part of the pipe is just under 11,000 Pascal. And this makes sense. The fluid's moving faster, so the pressure is going to be lower. In addition, the fluid is elevated, so that means that there's going to be a drop in the pressure as well as a result in the drop in the gravitational potential energy. Here's another example that's not found in your textbook. Water flows with constant speed through a garden hose that goes up a step 20 centimeters high. The cross-sectional area of the hose at the top of the step is half that at the bottom of the step, and the speed of the water at the bottom of the step is 1.20 meters per second. What is its pressure at the top of the step? We're told how fast it's moving at the bottom. It's 1.2 meters per second. And we need to figure out what its speed is going to be at the top. It's going to be moving faster because the cross-sectional area is less. And we know that the volume flow rate is going to be the same going into the pipe and coming out of the pipe. So let's figure out what the speed is in the upper section of the pipe. We know that the cross-sectional area of the upper part of the pipe is half that of the lower part of the pipe. Put that into our equation of continuity. So I find that the speed of the fluid in the upper section of the pipe is 2.40 meters per second. Now let's use that in Bernoulli's equation. Let's recognize that y1 is going to be equal to 0 and y2 is going to be 20 centimeters or 0.2 meters. Let's also recognize that they don't tell us what P1 is. I'm going to leave things in terms of P1. In fact, I think what I'm going to do is find what P1 minus P2 is to figure out what's the difference in the pressure at the top step. And now I'm going to try and put in the numbers. And now feed those numbers into your calculator. Recognize that you're dealing with water, and the density of water is 1 gram per cubic centimeter or 1,000 kilograms per cubic meter. And what I find is that the pressure in the upper part of the pipe is just over 4,000 Pascal less than the pressure in the lower section of the pipe. Now they were asking for what is the pressure. I don't know what the pressure P1 is, but whatever it is, P2 is going to be about 4,000 Pascal less.